Let's talk about Lagrange multipliers. It's a fiendishly clever optimization technique. And we use it when we have a function we want to optimize and conditions that control it. For example, suppose we start off with this simple function. F of xy equals 5x plus 3y. And you should be objecting. That function doesn't have a maximum or a minimum. It's a linear function. The graph is planar. It goes up and down forever in all directions. But let's suppose, for some reason, we want to restrict it. And the constraint is we want to maximize 5x plus 3y for points on the hyperbola, for some reason, x squared minus y squared is 16. That's our condition. This guy up here is the object function we're trying to maximize or minimize, and this guy right here is the constraint. And you'll notice that the constraint, well, I have it written equal to a constant, which is exactly what I want, and I'm going to give him a name. So I have my object, 5x plus 3y, called f, and I have my constraint, which is x squared minus y squared equals 16, a hyperbola I'm calling g. Now let's bring in our buddy, the gradient vector. The gradient for f is just 5, 3. The gradient for g is a little more complicated, but not very much more. 2x minus 2y. A lot of books insist that the constraint be written equal 0, but as long as it's a constant, you don't have to worry about the results. Now here's the funny thing. The Lagrange criterion, the requirement, is that these two vectors are parallel. One way to do it is just say, well, if they're parallel, one of them has to be a multiple of the other. And the traditional multiplier is lambda for Lagrange from the Greek alphabet. And I can put the g or the f on either side. It doesn't really matter. That's completely arbitrary. Notice what happens. I have now said that the vector 2x minus 2y is equal to lambda times 5, 3. If I write this in components, I've got 2x equals 5 lambda. I've got minus 2y equals 3 lambda. And that's two equations and two unknowns. I need a third equation. And here it is. It's my constraint. X squared minus y squared equals 16. 3 equations, 3 unknowns. I'm going to solve this now. So let's see. According to what I have here, x is equal to 5 lambda over 2. And this one tells me that y equals minus 3 lambda over 2. If I put these together into the third equation, I have 5 lambda over 2 squared minus negative 3 lambda over 2 squared, all equal to 16. In other words, 25 lambda squared over 4 minus 9 lambda squared over 4 equals 16. At this point, 25 lambda squared minus 9 lambda squared, we're looking at 16 lambda squared over 4. So I hope you can tell that lambda squared had better equal 4. Lambda squared had better equal 4. So lambda is plus or minus 2. If you take that back to what we had before, remember we had x equals 5 lambda over 2, and we had y equals minus 3 lambda over 2, if lambda is 2, well then I guess x is 5 and y is just minus 3. But if lambda is negative 2, looks like x will be negative 5 and y will be positive 3. X and y have to have opposite signs. Furthermore, if you go back to the object function, and you might remember that was 5x plus 3y, f of 5 comma negative 3 would be 5 times 5 plus 3 times negative 3, 25 minus 9, it would be 16. If you change the signs, no big surprise, you get negative 16. So it looks like we have max and minimum values of 16 and negative 16. And now I have a bad surprise for you. If we looked at the hyperbola in question, here's 5 negative 3 and here's negative 5 positive 3. One of these is a max and one of them is a min. It turns out 16 is the minimum and negative 16 is the maximum. And I'll show it to you this way. There is no good second derivative test or discriminant test to straighten this out for us. Look what I've done. I have put in level curves for the function 5x plus 3y. And when 5x plus 3y is equal to 16, it matches up to 5 negative 3. Notice, if you go this way, the function gets bigger. The function is getting smaller as you go this way. So this right here, that's a minimum. And as the function gets smaller and smaller and smaller at negative 16, it touches right here. And that's a maximum, because when you move further in, you go down even more. So you have a negative 16 maximum value and a positive 16 minimum value. And let's look at the picture just a little bit longer. The reason Lagrange multipliers work is that the level curves of the object function and the actual curves of the constraint are tangent right there. Points of tangency are points of optimization. And if you took the gradient of the object function, you would get a vector perpendicular to the line. If you would take the gradient of the object function, the constraint function, you would get a vector perpendicular to the hyperbola. So they would have to be parallel at those 2 points. And that was the Lagrange criterion. So having performed that magical bit of work, let's look at a slightly different problem. I have another image that shows an ellipse and another linear object function. We have points of tangency here, and there's going to be another one on this side as well. If we go through this process, for this particular problem, we have the following. The object function f of xy is simply 3x plus 4y. The constraint in this case, however, is a rather interesting looking ellipse, and the ellipse happens to be 9x squared, x squared plus 4y squared equals 13. And of course, since I messed it up there, I'm going to have to call this g of xy on this side. Okay? So now that we're looking at this result, let's check out the criteria as we have done before. Del f will be 3, 4. Del g will be 2x and 8y. When we put these together, and we have del g has to be lambda del f, we're going to have 2x 8y equals 3 lambda, 4 lambda, or 2x equals 3 lambda, 8y equals 4 lambda, and just like before, the constraint serves as our third equation with the third unknown. So we have x, y, and lambda. Again, x is 3 lambda over 2, and y 4 lambda over 8, or just lambda over 2. Okay, let's plug these in. If we plug these in, 3 lambda over 2 is squared. We have 4 times lambda over 2 squared, and that's 13. So what do we have now? 9 lambda squared over 4 plus 4 times lambda squared over 4 equals 13. We end up with 13. Lambda squared over 4 is 13. And somehow I have managed to create another problem where lambda squared has to equal 4. So lambda is plus or minus 2. If we go back to our conditions, we know that, remember, x was 3 lambda over 2, and y was lambda over 2, so lambda equal 2 says that x equals 3, y equals 1, and lambda equals negative 2 says x equals negative 3, and y equals negative 1. If we go back to the illustration, there we are at 3, 1, and here we are at negative 3, negative 1. The level curve right here is labeled 13. If you plug 1, 3 into the object function, and remember what the object function was. The object function was f of xy equals 3x plus 4y. If we plugged in 3, 1, we got 9 plus 4 is 13. And negative 3, negative 1 simply gave us negative 13. This one works out a little bit more the way we like, because this is a maximum. Check it out, 13. It's as big as you can get. Here's 16, 19, and 22. That's off to the side. And the values keep dropping and dropping until right here you're going to hit the minus 13 value. One more thing to mention. Check this out if you want to do this problem by substitution, using a parameterization of the ellipse right here, plug into the object function, and get a new way to do it. But that's not the task we're looking at now. We're using Lagrange multipliers.